Okay, so this is problem 7.67, and for this problem we have a cascade of two common source amplifiers, and the first stage is fed with this signal with a resistance of 200 kilo ohms. In the second stage we have a load resistance of 10k ohm connected at the drain of the second stage. Part A, it asks us to sketch the equivalent circuit. So the first stage, we have this signal connected. So this is this signal. Okay, we have the resistance, which is 200k ohm, and that goes here, and that's basically what gives us VGS1. This VGS1 is used by this current source here to define the drain current. Okay, so the value of this current here is GM times VGS1. And this current source, it connects directly to the drain resistance, so RD1, and that is connected to the second amplifier, so goes to the gate of the second amplifier, and that gives us plus or minus VGS plus minus VGS2. So let me put plus minus here. Okay. Now this VGS2 is going to be used by the second current source here to give us the value of ID2, which is GM, I could say GM2 times VGS2, and here is GM1. Okay, they might be different if we have like different, if we have a different drain current. And this one here is connected to the drain resistance 2. And remember that this terminal here is the drain. So for the second stage up here, we have also a load connected. So this is our load, and this is our V out. So that's the circuit. Okay, that's the circuit that we need to sketch. So we have our input signal here that changes the voltage VGS1 based on the biasing circuit that we are using for each one of those MOSFETs. We can define a GM1 that will gives us a current small ID1 flowing here. Okay, this current will basically force a voltage drop across this RD1. That voltage drop is actually VGS2. This VGS2 is being read by this second stage here, right? So this is the gate of this is gate 2. To define this second drain current here, that is the transconductance of this second transistor, this second amplifying stage, times VGS2. And this VGS2, this GM2 VGS2 will give us a drain current here, and the equivalent resistance of those two here times this drain, so it's not capital, it's small, this ID2 here will gives us the output voltage. Okay, so that's the working of this circuit. Okay, now for the second part, and given that the drain current on both, so the capital ID, okay, which is the DC drain current, is 0.3 milliamps for both transistor, and that the voltage, the overdrive voltage is also the same for both transistors, and it's 0.2 volts, and RD is equals to 10K for both resistance, we need to find the overall voltage gain. So V naught over this signal. Okay, and I'll go up here and I will start doing some analysis for part B. Okay, so in this first loop here, in this first part of the circuit, we know that because there's no current flowing through the gate of the first stage, or there's no current flowing here and there's no current flowing here, right? Because there's no current flowing through the gate of the transistors. We conclude that in this case here, in this part of the circuit, VGS1 is actually equals to this signal, right? And from this analysis here, from this part of the circuit, we know that VGS2 is equals to, so because we are assigning plus minus here and the current flowing through the drain is counterclockwise, this means that this VGS2 is actually minus GM1 times VGS1, okay, this part here, times RD. And I'm calling just RD because we know that RD1 is equals to RD2, okay? But it could be RD1. And from this equation here, right, from this analysis, we can substitute VGS1 here. So we find that VGS2 over this signal is equals to minus GM1 RD1. So that's the first equation, okay? So let me copy this equation down there. Oops. So that's the first equation that we have. VGS2 over V signal 1. Okay, so just erase this part here so we can reutilize this circuit. Okay, let me simplify some drawings. Okay. Now for the third analysis, let's go over this last part here in the circuit, right? So we can write an equation for V naught, okay? So, or the output voltage. So the output voltage, let me use red now. The output voltage, okay, so because we have this current ID here going counterclockwise, and we define V naught with current that should be assigned in this direction. V naught is actually minus GM2, which is ID2, VGS2, times the parallel between RD2 and the load resistance, right? Because this current ID here, part of this current is flowing here, part of this current is flowing there, they add here at this node to form this ID2. So if we take the parallel of those two, we basically represent as a single resistance, and over across that single resistance we have ID2, which is this one here. And this minus, remember, is just because the way we have assigned V naught here. So we are measuring V naught with this polarity here, which from the positive sign convention it would basically means that we have a current flowing in this direction. But because this voltage source forces the current to flow counterclockwise, we have to take this minus sign. So from this part here we can isolate V naught over VGS2, and this is equals to minus GM2 RD2 times RL divided by RD2 times RL. And that's the equation for V naught over VGS2. So let me copy this one here and put it down there. What I'm doing wrong? Okay, so let me use. Now it worked. So we have these two equations, okay? Now if you look at this equation here and this one here, if we multiply them, so if we take VGS2 divided by V signal times V naught over VGS2, this gives us VGS2 cancels with VGS2, V naught over this signal, which is, so minus GM1 times minus GM2 gives us GM1 times GM2, because minus times minus gives us plus. So RD1 times RD2 times RL divided by RD2 plus RL. And that's the equation for the overall voltage gain, right? So if we look at the known values here, we know RD1, RD2, and we know the drain current, we know the overdrive voltage. So it's just a matter of calculating the transconductances, and we are good to go. Now, how do we calculate the transconductances? So remember that the transconductance is equals to 2 times ID divided by the overdrive voltage. And this is 2 times the drain current, that is 0.3 milliamps, divided by the overdrive voltage, that is 0.2 volts. And those are known values from the problem. So this one here and this one here. So this gives us a transconductance of 3 milliamps per volt. And because the drain current and the overdrive voltage is the same for both transistors, this GM is actually the same. So V out over V signal, which is equals to our overall voltage gain, is equals to 3 milliamp squared times RD squared, because RD1 is equals to RD2. And actually The load resistance, if we go up there, is also 10K. So this gives us RD, or let me substitute 10K cubed divided by RD2 plus RL, which is 20K. And this gives us an overall voltage gain of 400 volt per volt. And it makes sense that now it's positive, because remember that the voltage gain for an amplifier, it's negative, right? So it's usually minus 15 or minus 14 for this particular common source amplifier. But because we are connecting two in cascade, we are cascading two common source amplifiers, the first stage gives us a negative gain, and the second one gives us another negative gain based on the output voltage of the first stage. So we basically have a positive gain, an overall positive gain, and in this case of 450 volts per volt.